Welcome back. We'll try example 2. Evaluate integral negative infinity to 0 x times e to the x dx. And this part of the video is part 2, part B of 7-8. We are going to be showing some examples of type 1 and type 2. Evaluate integral negative infinity to 0 x e to the x dx. So first, this is improper integral type 1. It's improper because the lower limit or upper limit is infinity and or negative infinity. Lower limit is negative infinity here. And it is type 1 because the interval over which the integration is done is an infinite interval. So it is from negative infinity through 0, which is an infinite interval. So the integration is done, evaluated over an infinite interval. So it is type 1 improper integral. So whenever you do improper integrals, you know that you have to use a variable t and then allow t to approach infinity or negative infinity, whatever the case may be. Here we are going to call the given integral as I. I is negative infinity, integral negative infinity to 0 x e to the x dx. Then we want to write the way we write the improper integral, t approaching negative infinity limit, and then you change wherever the infinity or negative infinity occurs as t, then it is t to 0 x e to the x dx. Now we will take only, we will have to get back to this step. This is step 1 in the problem, identifying as an improper integral and then allowing the limit, using the limit to write down the improper integral. Step 2 is to evaluate the integral. In this problem, we are going to be just considering this part without the limit. Then we will get to the limit when we get to step number 1. So it is x e to the x dx, and then it's a combination of algebraic and exponential. So you're going to apply integration by parts, integration by parts. So u equal to x and dv equal to e to the x dx. So du is dx, v is integral of e to the x, which is e to the x. So it is uv minus integral v du. So u is x, v is e to the x. Here remember, it's a definite integral, so it e to 0 minus integral v du is t to 0. So if I expand that to 0 times e to the 0, so which is equal to 0, then at the lower limit, it is t times e to the t. That's negative t to the t minus integral of e to the x is e to the x between the limits t and 0. So that turns out negative t e to the t minus e to the 0, which is 1, minus e to the t. That becomes negative t e to the t minus 1 plus e to the t. Now, coming back to step number 1 in I, if we get back to I, which is limit as t approaching infinity, t approaching negative infinity of t to 0, integral t to 0, x e to the x dx. But this integral is what we computed here, and that turns out to be this negative t to the t and all that. So it is limit as t approaching infinity of negative t e to the t minus 1 plus e to the t approaching negative infinity. So t approaching negative infinity e to the t is e to the negative infinity. E to the negative infinity is going to be 1 over e to the positive infinity, which is equal to 0. 1 over a large number, which is equal to 0. So this is equal to 0. Now this part, then you have a negative 1. This part, the first one, uh, when you substitute negative infinity, it becomes negative of negative infinity times e to the negative infinity. So that is kind of indeterminate. So if you do limit as t approaching infinite, negative infinity of t times e to the t is negative infinity times e to the negative infinity is negative infinity times 0 is indeterminate. So we cannot assume that to be 0 or negative infinity. Whenever you have such an indeterminate quantity for limits, we can apply L'Hopital rule. So we are going to do this part separately, which is the one yellow highlighted. The limit as t approaching negative infinity of t e to the t, which is equal to limit as t approaching negative infinity. It is indeterminate product, so we have to make it to quotient, that is t divided by e to the negative t. E to the positive t can be written as e to the negative t in the denominator. The idea here is we want to apply L'Hopital rule, and L'Hopital rule applies only to indeterminate quotient. We want to bring it to the quotient form. That's why we write like this. Now you take the derivative of the numerator and derivative of the denominator. Derivative of the numerator over derivative of the denominator. The limit as t approaching negative infinity. The numerator is derivative is 1. Denominator is negative e to the negative t. We are applying chain rule. So when you apply negative infinity, so it is going to be 1 over negative e to the negative of negative infinity, that it is e to the positive infinity. So that becomes 0. So by applying L'Hopital rule, we are able to prove the part in this step, in this one, t e to the t approaching negative infinity becomes 0. So now, getting back to that step 2, that limit, so we get substituting the 0, substituting this limit equal to 0, we get I equal to limit as t approaching negative infinity. We are actually using the step number 2, t approaching negative infinity, integral t through 0, x e to the x dx equal to um, limit as t approaching negative infinity, negative t e to the t minus 1 plus e to the t, but this was 0. Now, from what we have proved, this first expression is also 0. So, ending up with the value equal to 0 minus 1 plus 0, which is equal to negative 1. So, the improper integral by our computation here turns out to be negative 1. So, the improper integral is actually convergent. The question is not about convergence or divergence. The question is to evaluate. So we just say it's equal to negative 1. If you're also asked to determine whether the integral is convergent or divergent, then your answer would be that the improper integral is convergent because this value is a finite value. Hope this video helps.